So my first proposal to NSF, in which I wanted to study nitrogen in the ocean, was to study nitrous oxide. One of the reviewers wrote, "Brian's a carbon isotope guy. He can't do this." Fortunately, you know what? Think about the spectra of nitrous oxide. You know, what are the masses that you measure? 44, 45, and 46. You actually fool the mass spectrometer. It thinks you're measuring CO2. So, never mind. All right, so nitrogen in the ocean. What we're going to talk about are the inputs and the outputs, what controls those and what controls the fractionation. For the inputs, we have nitrogen fixation, as well as terrestrial sources, either via rivers or atmospheric inputs. For outputs, there's sedimentation. Organisms fix nitrogen, they settle and get buried. So that's one way in which nitrogen is removed. But also there's denitrification, the reduction of nitrate to N2 gas and the flux of that N2 gas out of the ocean. That can occur both in the water column and in sediments. And the carbon isotope fractionation associated with sedimentary denitrification and water column denitrification is very, very different. Okay, but before we get into that, first let's just look at nitrogen inventories. All right, so most of the nitrogen is in the atmosphere as N2 gas. We've got nearly 80% of it. There's another 20% locked up in sedimentary rocks, sort of as nitrogen and organic matter and inorganic matter. In the oceans, the major form of nitrogen is again N2. It's dissolved nitrogen, and it's about 0.5%. Nitrate, which is biologically available, doesn't even show up here in terms of a percentage at one significant figure. Soil organics, land biota, marine biota, again, are very, very small. So we think about less than 0.5% of nitrogen on Earth is in the ocean. Why do we even bother studying it? Turns out that, of course, nitrogen is an essential nutrient, and it limits production in many areas of the ocean. And these sources and sinks are dominantly biological. A lot of the cycling and the exchange is internal. And the isotopic composition of nitrogen in the ocean allows us to place constraints upon those inputs and outputs as well as the biological cycle. Now, earlier last week, Jed showed you this scary diagram on nitrogen, oxidation state, and the different forms of nitrogen and the different reactions that occur. And, just starting here with nitrate, it can be assimilated via nitrite to ammonia into organic nitrogen. Catabolism releases that, and then through nitrification, it returns that back to nitrate. Nitrate can also be denitrified, nitrite to N2 gas. There can be some nitrous oxide leaking out of that, and then there's N2 fixation. And then there's this recently discovered reaction, anaerobic ammonia oxidation. Under anaerobic conditions, ammonia or ammonium and nitrite can react together to produce N2. There are isotope fractionations associated with all of those, and some of those isotope fractionations are bizarre. They're big, equilibrium isotope fractionations of 60 per mil. We have inverse kinetic isotope fractionations associated with some of these reactions that are like 30 per mil. The place where these reactions occur within the oceans is different. In the surface ocean, there's N2 fixation, there's assimilation that gets exported. As it gets altered, you produce ammonia. There's oxidation of ammonia to produce nitrate. That nitrate can be denitrified both in sediments as well as in the low oxygen regions of the ocean, these so-called oxygen deficient zones, or ODZs. That's regions where water circulation is slow plus production is very high. So there's segregation of these different reactions, and again, there's isotope effects associated with all of those that are quite complex. Okay, so a few facts. Half photosynthesis on Earth is marine. Most of it's in the deep ocean, sort of this deep blue sea, the invisible rainforest, as it's been called. By virtue, not because of high production, but because of the vast area that we're talking about. So certainly production rates are highest on the continental shelf, but most photosynthesis occurs off those small shelves. The controls on production in the ocean are very, very different than on land. There are very high rates of organic matter production. There's high turnover, and the essential nutrients that drive that production are in many cases barely measurable in the surface ocean. And production is maintained not by the supply, so much by the supply of nitrogen to the system, but by recycling. And there's something peculiar about marine organic matter in that there is a constancy to it. And this was noted a long time ago by somebody named Redfield, this Redfield ratio, this carbon to nitrogen to phosphorus ratio, and phytoplankton, as well as in inorganic nutrients in the ocean, maintain this constant ratio, 106:16 to 1. The 16 to 1 ratio in between nitrate and phosphate is particularly useful in trying to decipher what overall controls are on inputs and outputs from the ocean. Okay, so if we think about it in sort of box model space, most of the recycling occurs above the thermocline. Up to about 80% is recycled here. Some of that organic matter is exported, and there's continued recycling. When that occurs, those nutrients, or the inorganic nutrients that are released, eventually get returned to the surface, and that's what has been termed new production. So it's new production, even though it's recycled, it's new to this thermocline because it comes up via the deep ocean. And it's returned to the surface ocean. There are two sources of externally supplied nitrogen to the ocean. One is nitrogen fixation by diazotrophs and atmospheric deposition. Pre-industrial, nitrogen fixation was the dominant supply of nitrogen, new nitrogen, or completely new nitrogen, this external supply. But atmospheric deposition has become much more important in recent times. There was an article, I didn't quite get a chance to snitch some of the figures from it, but it's on organic matter in coral from the South China Sea. And the isotopic composition of the organic nitrogen in these corals was measured over the last, 40 years or so. Well, corals grow, they have these annual bandings, so you can count those bands and you can isolate the organic matter and analyze it. And the nitrogen isotopic composition of those suggests that the changes in the nitrogen isotopic composition have been related to atmospheric deposition over other supplies, such as nitrogen fixation or the supply of new nitrate from deep water. It's a really interesting paper. It's sort of arm waving in that it uses some gross isotope mass balance, but the numbers are so big that it's really difficult to argue that over the last roughly 20 to 30 years that in the South China Sea, atmospheric deposition of nitrogen is a new nitrogen source to this isolated reef environment. So I think that's one of the first good, solid pieces of isotopic evidence that I've seen for the flux of atmospheric deposition influencing this ecosystem. Okay, now because there is respiration at depth, we do have profiles. These are nutrient profiles. Nutrient concentrations of nitrate are low at the surface, increase at depth. They're low because there's uptake. They're high at depth because there's respiration releasing those inorganic nutrients. In the deep ocean, so here, this is micrograms nitrogen versus depth in the ocean. These are kilometers depth. The western and eastern Atlantic have lowest concentration, highest concentrations in the western North Pacific. Why is that? Why are concentrations higher in the Pacific of nitrate than in the Atlantic? Okay, remember Saturday's lecture? The big circulation picture, thermohaline circulation. Where are the oldest waters in the ocean? In the Pacific, yes. So if you've got organic matter raining down as this water is flowing through the deep ocean, it's taking 1,000 years. By the time you get to the Western Pacific, there's a lot more organic matter that's been remineralized. So nutrient concentrations are higher because there's been more respired organic matter releasing those inorganic nutrients. So similar to the inorganic carbon delta 13C story that Howie told. Okay, so inputs of nitrogen, let's put some numbers on this. Bacterial nitrogen fixation around 90 to 160 teragrams of nitrogen per year. There's a small isotope fractionation associated with nitrogen fixation. So the particles that are formed are -4 to about -1. As nitrogen is dissolved in the ocean, there's an equilibrium fractionation where there's an increase of about 1/2 per mil. So with a small fixation, we get isotope effect associated with fixation -1 to about -4 for the particles formed. Bacterial nitrogen fixation can also form on the seafloor when light reaches down to those shallow regions, but it's a small amount. The values are about the same. We also have inputs through riverine, 40 to about 50 teragrams nitrogen per year. The isotopic composition is poorly constrained, and it's variable depending on where that nitrogen's coming from. But generally it's thought to be about 0 to 3 per mil. Atmospheric deposition, increasing, but about 70 teragrams per year. It may be higher in some regions. Again, the isotopic composition is not well constrained. I think the paper for organic matter in the South China Sea used a value of pretty close to 0, but I don't remember if it was +2 or -2. But it's pretty poorly constrained. Mostly measurements of either nitrate or dissolved organic nitrogen in rainwater.
I have a question.
Yeah.
What is the process causing the fractionation of riverine inputs? I mean, it's in
The fractionation is not a fractionation. It's just this is a delta value, the source of nitrate in rivers. So yeah. Again, same with atmospheric deposition. Outputs of nitrogen include denitrification, nitrite oxidation, and anammox. The fractionation for these are, not for nitrite oxidation, but for anammox and denitrification, around 10 to 30 per mil, 20 to 30 per mil observed in the field. The big regions are the Eastern Tropical Pacific and the Arabian Sea, with the Eastern Tropical Pacific being greater, about 50 teragrams nitrogen, about 30 teragrams nitrogen per year in the Arabian Sea. The biggest loss is through benthic denitrification. This is denitrification that occurs in surface sediments. And the fractionation is effectively 0 because of complete utilization of nitrate below that sediment-water interface. So unless some form of nitrogen other than N2 gas leaks out, the fractionation is effectively 0 because it's acting like a closed system. Okay, and then sedimentation, so fixed nitrogen falling as a particle and being buried is a small term in terms of the output and a fractionation that remains constant at about 5 per mil. Okay, so pretty straightforward. Yeah?
How about in anoxic system like in microbes?
I'm sorry.
How about anoxic ecosystem?
How is
Anoxic.
anoxic?
How is the fractionation of nitrogen?
For?
Anoxic areas
Anoxic
in the
areas.
mangroves.
Oh, I'll talk about that in more detail. So there's no simple answer to that question. How does anoxic regions of the ocean, what's fractionation associated with the anoxic regions? In general, fractionation associated with denitrification within the water column is relatively large, 20 to 30 per mil. But we'll look at experiments on what controls that in a moment.